everyone, and welcome to the webinar. I'm going to run through the agenda very quickly with you. So firstly, we've got a very interesting and valuable webinar that we want to share with you today. I will do the welcome and introduction, which will be done by myself. Then I'll introduce you to some speakers that we have today. We've got an introduction to sustainable manufacturing. I think sustainable manufacturing has been a big thing. We're seeing it with quite a bit of our clients and manufacturers out there. How can it be more sustainable, and what are the steps to consider in that? That follows on to the 6 considerations. We've got a question and answer session following that, and of course a close. Now, just to give you a quick introduction, my name is Daniel Balaram. I head up the manufacturing and process plant industry segment here at Baynes. I've been in the Autodesk industrial channel for over a decade now, various background predominantly in mechanical engineering. However, a career spanning in the Autodesk world around data management and product design and manufacturing. And I want to take you through who we are. So at Baynes, we are a niche consulting company that specializes in various industries, as you can see, from the building, civil, energy, process plant, as well as manufacturing. And how do we do that? We've got a very unique way of doing it. We look at 3 areas comprising of consulting, which looks at tools like business process assessment, BIM consulting, data management, CAD, CAM, which you're going to hear more of a bit later, as well as simulation. And from an education perspective, we believe strongly in a blended learning approach, which comprises both of classroom as well as online self-paced learning. And from a hardware and software perspective, we are Autodesk Gold partners, Leica partners, as well as Clear Edge partners. Not forgetting, we have supporting brands that support the workflows that we consult on. So tools like Clear Edge, Leica for your scanning, Cool Orange for the Vault, as well as Open Space for reality capture. So to take you through to the main event or the main speakers for today, I've got my colleague Peter Watson, who is quite a stalwart when it comes to the CAM industry in South Africa. He's got quite a bit of experience within the CAM environment as well as the design environment. He is a certified instructor as well, of course, a seasoned Autodesk professional, and he's very passionate about machining and fusion in specific. Following to Peter, we've got Michael Smith, who is our application engineer and on the CAM and CAD solution side of it for manufacturing. Michael is a seasoned professional, again, with CAM. He specializes in machining as well as post-editing and post-configurations. He's got quite a bit of experience in the manufacturing environment, specifically around furniture and metal manufacturing. He has an honors degree from the University of Pretoria, and he enjoys designing and working with his hands. Okay, so without further ado, I'm going to hand you over to Michael, and then Peter will join in shortly.
Okay, good morning, everyone, and thanks so much for joining this webinar on sustainable manufacturing. Yeah, so we all know that sustainability is a big buzzword at the moment, and everybody is gearing up towards a more carbon neutral and potentially carbon negative carbon footprint as we try and reduce our impact on the natural environment. Yeah, just share some charts and graphs. We've all seen these before. Yeah, the levels over the past few decades, the levels of atmospheric carbon dioxide is rising, global sea levels are rising. Yeah, there's definitely an upward trend where values are moving in a direction which is not going to lead to a habitable planet in a few decades if things are not, we don't flatten the curve, as it were, of these increases. We're already seeing very extreme weather conditions. Yeah, like the heat waves in Europe at the moment, several floods and massive hurricanes happening. There are changes that are visible. It's not something that certain scientists are just fear-mongering about. These are real things that are happening in our world. I'll hand over to Peter, who's going to talk a little bit more about the industry and how it is being affected.
Hi everyone, my name is Peter Watson. Once again, thank you for joining us today. Yeah, the statistic that's up here on the screen here, it highlights a significant impact of manufacturing and production sector on global carbon emissions and energy consumption. And obviously this is worldwide. It underscores the sector's substantial contribution to both environmental challenges and energy demand worldwide. Reducing emissions and improving energy efficiency in manufacturing are critical steps to addressing climate change and sustainability goals on a global scale. We're all responsible for this, especially in manufacturing as well. And there are certain things we can put in place to lessen that impact that we have on the environment.
All right, so we'll have a quick look at the benefits of sustainable practices. The first point, of course, obviously the most important benefit of sustainable machining is to reduce the environmental impacts manufacturing is having on the planet. By reducing the carbon footprint of your workshop, manufacturers can contribute to the global effort to reduce the carbon emissions and slow the rate of increase of CO2. Then moving to the next point, there is an economic benefit to implementing these sustainable practices. Reduce wastage of material results in less money spent on materials. Recycling of waste materials will also reduce that amount spent. And of course, lower power consumption means lower electricity bills, less amount spent on powering your machines and devices. And yeah, we'll look at some strategies to implement that. Then of course, yeah, a lot of people are, especially the younger generation, are really conscious about what the carbon impact is of many companies. If your company is geared more towards a sustainable approach and are using sustainable practices, yeah, it will improve your brand representation. Yeah, you'll have more credibility out there because you're making a difference, you're trying to make an impact, and you can respond to these very clear changes. Yeah, then of course, meeting regulatory requirements. Actually, just this week, Cyril Ramaphosa has signed into law the climate change bill that sets out the national climate change response, including mitigation and adaptation actions. And yeah, it's going to help South Africa move towards reaching the goals that are set out by international standards. I think this is a really positive thing for our country. Okay, so that brings us to our 6 steps. So we've set up these 6 headings that we're going to look at these different ways of enacting these sustainable practices. What can we practically do in the workshop? What are the subjects we can consider to move us towards a more sustainable approach and to reduce our carbon footprint? The first one is what are the causes of waste material in the workshop? First, we can look at programming errors. If you're perhaps machining manually, standing at your machine and programming, or you don't have accurate simulation, you might end with programming errors, which of course then you cut the part incorrectly, you have to discard that piece. Yeah, it's a huge cost financially, and it's wasted material that will then have to be or potentially be recycled or repurposed if possible. Then another cause is machine collisions, again relating to simulation. If we don't have an accurate simulation of our machine, we have to run things live, to doing a dry run or something, and yeah, there's always mistakes that can occur. We haven't simulated correctly. We see the machine colliding, and it collides into your part. Again, you've got a lost part. It's going to waste your time. It's wasting your money and material. And then again, tool collisions. If your tool is not correctly set up in your simulation, you could have problems there. If you're programming by hand and you haven't factored in the length of your tool, the diameter of your tool holder, these are all things that could potentially result in crashes and lost material. But yeah, let's have a look at some animated simulations that are produced in Fusion. I'll hand it over to Peter for that.
Thank you, Mike. Okay. All right, as you can see on the video that's playing in the background here, I've given an example of this is now a rapid collision into the side of the stock. The sad point is it's actually fairly common. This is something that a lot of the guys in the workshops have seen. It's a very easy mistake to make as well, especially if, for example, your operators are manually punching in code onto the control, for an example. You have no foresight into seeing these things happen before they actually occur. Once your machine crashes, you've now wasted a tool. That's extra material. It's another tool that needs to be made. And obviously, all these things that will add up have a massive impact in terms of the environment. The whole point is to try to be more efficient. That's probably the best thing we can all do in manufacturing to help us for the future. Okay, so yes, one decimal value. If, for example, your guy makes one comma in the wrong place, forgets to put a positive or a negative, that can then go and send your spindle in the complete different direction. And like I was saying earlier, they're very easy to mistake to make, especially the guys on night shift, for example. Guys are tired, production's heavy. These things happen every single day as well. The whole point of what I'm showing in the background here is that you've got a simulation on a table. This example was on a Haas, and we can actually see now before this happens on the machine and actually rectify that error before we have the problem there in the workshop. It's essentially a digital twin. It eliminates a lot of risk, as well as giving your operators more confidence to learn, to take more risks. You know, if they make a mistake in the software, you can just Control Z, you can undo and go back again to get your clearances better, to try and improve your machining times. But when you're doing it physically on the control, on the machine, it's a massive risk, not only to the owners who own these machines and pay for them, but also to the operators who don't want to crash them. That's in engineering, you don't crash machines. So it's not only just going to make you more efficient, but it's going to allow you to take more risks, to push your machines a little bit. Because again, the mistake is not a big financial consequence. Okay, let's just get this one on the go. So this was another example where we can see our holder is now going in. It's obviously now plunged way too deep down. Our tool is the incorrect length. And we can see now how it's basically showing us that our holder is now hitting the side of the job there. Another massive problem, I would say, in the industry is your efficiency is determined by the experience of your operator. You get a guy who's brand new, who's only been there for 1 year versus somebody who's been machining for 50 years. That has a massive impact on how efficient your workshop is going to be. And again, if the guys have got something like CAM software they can practice on, they can make mistakes with, it really will speed track their development process as they go along from a very early stage as well. And again, if you do have a crash, you have a 3D model of your machine as well as your work holding or your work holding devices like your vices. So you can actually have a 3D model of your vice in the software so they can make sure clearance, that when the machine now comes over the top of the job, there's enough clearance to clear that vice. Another common one, where the tool hits the side of a vice, for example, that didn't count for the extra height that you need for the clamping device, for example. Again, you can have this all simulated, have a one-to-one of it directly inside of your software. And again, you can undo it on a computer, but once that machine hits, it's too late. You've now crashed that machine, broken the tool, probably the holder. And as we know, to get these guys to come out and fix these machines can sometimes take up to a month, where your production is now standing still. It's a massive problem. Okay, what I'm doing in this video in the background here is I'm just showing that, again, once you've seen an error, you can easily come inside here. I'm basically just changing the height because we saw the height was incorrect. And again, it gives you control. So you can see exactly now and fix these errors before they actually happen on the machines. These simulations will also take into account your tool length as well as your rapid movements. So you'll get a blue line, for example, where the tool is now engaging into the material. You get the green lines, which are linking parameters, which is where your tool is just moving around the job. And then you also have yellow, which will be determined by your rapid movements, where the machine is now going to fetch another tool, for example. So you can see every single portion of that job and make sure it's 100% before you then send it off onto the machine. Visual representations of your tooling will include the type of tool being used, the number of flutes, you can obviously set that as well or edit it, the geometry of the tool, taking things into account like your diameter, for example, your shaft diameter, your flute length, corner radiuses. And again, if you've got a nice representation of your flute length, you can then get a much clearer indication as to your depth of cuts. Tooling has also come a long way over the last couple of years, and full flute length cuts for roughing operations is not uncommon. But a lot of guys I see are still doing these 10mm step downs because they're worried about breaking the tool. So we always say, rather make your tool pass more efficient, try use as much of your flute length as possible, remove as much material as you can. Your machine will be or won't be on for as long, and obviously it will save you a lot of energy at the same time as well. Just push, let me just go to this one here. Okay, so here's an example that I'm showing here where we can edit our tool, and all of your diameters and dimensions and your cutting parameters are all going to be shown here, which again you can edit and get it to be exactly the same as what you have on your physical machine. Okay, so the other thing I wanted to note here is obviously, yes, this comes in handy for collision checks to make sure your tool is the correct length. Also taking into account bigger step downs for more efficient tool parts on roughing operations. You can also then input your cutting data, like your spindle speed, surface speed, your feed rates, your lead in and lead outs, vertical rates, plunging. So you can also then get a very good, accurate machining time per operation or for that whole setup. And again, you can see if I'm going to make a change to the tool, I'm going to take a bigger depth of cut. How is that going to affect my machining time? Is it going to make it faster? Am I going to be more efficient? Am I going to save time? And again, time will always equal money as well. So again, you get an accurate feeding time, or if you enter the correct values, you can get an accurate machining time to then obviously see, are these changes actually making you more efficient down the line? Okay, next up, we're going to be talking about energy efficiency. So I'm going to hand back to Michael.
Yeah, so the next of our 6 points is energy efficiency. So yeah, as we saw earlier, 54% of energy consumption globally is used up by the manufacturing and production industry. So this is a pretty huge percentage. So yeah, obviously it's very important to try and see where we can minimize our energy usage, how we can improve the efficiency of our machining operations, our tool piling. Yeah, because our CNC machines they use quite a large amount of energy in the workshop. In fact, according to a statistic, 80% of power usage from your CNC machine is due to auxiliary components like your coolant conveyors, etc. Minimizing your non-running time is also quite important, because as your machine stands, you've got these auxiliary things running in the background. It's still using up a fair amount of power, even though you're not actually cutting anything. Yeah, strategies we can look at. Yeah, are definitely looking at more efficient tool paths, how to waste less time by cutting, less air time. So if you've got a more simplified, refined tool path, you're going to spend less time actual cutting time. But again, yeah, improving or reducing the amount of time that the machine is standing, not running. Yeah, again, we can go back to having accurate simulations and having a customized post-process, because how many times in the workshop do you send a file that's been generated by your program, you send it to the operator, and the operator reads through the code, and they see, okay, we need an optional stop there, we need to change, this is the wrong sort of drilling cycle type, and he's standing there, inevitably the machine is running while he's quickly making these changes on the controller. So Fusion has an excellent post-processor editor where we can customize the post, we can customize that NC code, G code output to output exactly the right codes that you need. That will then reduce this wasted sort of operator time, wasted machine time, where edits are having to be made on the fly. Yeah, this also reduces the risk of crashes happening if your operator is manually editing code. Yeah, there's always the added risk of accidentally erasing a line. We've lost a homing line, and which could result in a machine crash. All right, so here's an example of how, another aspect we can look at is accurately modeled stock. In this image on the left, we've just modeled a cylinder stock because that's quick and easy to model. And then, of course, our resultant tool parts, you can see that it's ridiculously complex. It's spending all this time machining away this material. So that's going to spend a lot of time. But the example I want to show is, okay, what if we use the cast part? Fusion has the ability to define the stock as a solid model. So here, if in actual reality, our stock is correctly modeled, when we add that clearing tool path to give a roughing around our part, we can see that the length of the tool path is greatly reduced, and for the cutting time, it's far more reduced. So having this accuracy of modeling, accuracy of simulation contributes greatly to the efficiency of the tool path. So we result in a much faster machining time we're not spending time machining the air. Okay, next we're going to be looking at cooling strategies, and Peter is going to take it from here.
Okay, cooling strategies. Coolant, very common, obviously, and the whole point is, why do CNC machines require coolant? There's several important reasons, namely heat dissipation. During your machining operations, the cutting tool and your workpiece generates significant heat due to friction as that tool now moves along the surface. Coolant will always help to dissipate this heat, preventing overheating of the tool, your workpiece, as well as your cutting zone. Overheating can also lead to dimensional inaccuracies, premature tool wear, and even damage to your actual machine. Another reason for using cooling would be, or coolant, would be to increase the lifetime of your tool by reducing friction and heat, obviously, as we discussed earlier. Prolonged exposure to heat without adequate cooling can cause tool edges to wear down quickly or even to soften. Again, that's going to mess up your surface finish. It means you can't take bigger depth of cut. Also for chip removal, it helps flush away the chips or your metal shavings and your debris generated during machining. Efficient chip removal prevents chips from accumulating in the cutting zone, which can cause tool breakage, poor surface finishes, or interfere with subsequent machining operations. Another reason would be for reduced workpiece distortion. Intense heat that's generated during machining can cause thermal expansion and distortion of your workpiece and material. As we know, cold things shrink, hot things will expand. Coolant helps maintain more consistent temperatures, reducing the likelihood of your workpiece distortion and improving your overall machining accuracy. Okay, so the problem with coolant, it can have, obviously it's got its negatives and it's got its positives as well. The selection of your coolant will play a critical role in determining the sustainability of a machine's operation. Whether it has positive or negative impact hinges on several factors that influence your efficiency, longevity, and of course your environmental impact. By carefully considering the properties and implications of different coolant options, manufacturers can significantly influence the overall sustainability of their operations. This choice not only affects performance, but also contributes to the broader environment and economic goals. Thus, understanding the ramifications of coolant selection and of course the disposal are essential for achieving sustainable machine operation, specifically the disposal part. Okay, so what is it made of? And we can see there that formaldehyde. Chemical composition. So coolants contain lots of chemicals such as harmful oils, biocides, corrosion inhibitors, and of course formaldehyde. Sadly, this is quite common in most coolants that guys are using in the industry today as well. It's extremely harmful to the environment, especially to the operators as well. If you look at some of the guys who've been in the industry for a while, who've had their hands in that coolant for many years, you just look at their hands and it can actually tell you pretty much straight away just how dangerous this chemical is. These chemicals can be toxic to aquatic life if they enter waterways through improper disposal or leaks. So I know most guys in the December shutdown will do cleaning of the machines when it's quiet and actually go flush out their machines, the guys who actually do it. If you've ever looked inside your CNC machine's tank after a year and see what's living in there, it can be quite scary. I've even seen people going and actually flushing that out and literally pouring it down the drain. Please, it is so important to look at how do you dispose of your expended coolant. This should not be being poured down the drain. Sorry, coolants can come, so also your coolant material over a year, for example, it becomes very contaminated with metals. You take all the shavings that have gone there, particulates, and microorganisms during your machining operations. Your operators go in there for a second setup, turning the part around, they got their hands in the coolant, and if you had to zoom in onto your hands, it can be quite scary to see what lives on us every day. That obviously now goes into your machine's tank and lives there in its own environment, this little biodome for a year, which then gets flushed and poured down the drain, which is obviously not good for the environment. Very important to be taking care of this properly. Waste generation, the big advantage here as well is your coolants are often used in large quantities. If we take a 3-axis mill on average, we're talking about 100 liters of liquid. Some of these machine shops have got 30, 40 of these machines. That's a lot of chemicals. That's a lot that's been poured down or not disposed of properly, and that obviously has a massive impact onto our environment as well. Okay, so I think next we wanted to do a little poll just to get an idea for the guys that are doing machining or have CNC machines. To get an idea, I'll leave it on for a few minutes. If we can just complete this poll, we'd like to get an idea as to how you guys are currently doing it. Okay, it should be coming up. Okay, thank you to everyone that voted. Some interesting results there. Obviously, as expected, we've got a lot of flood and dry cutting. Yes, those are the two most common. Interestingly, I saw we had 13% on cryogenic, which is quite interesting. I was watching those the other day. Very interesting way of seeing it. If cryogenic is something new that you haven't heard of, I do recommend to go and that's worth a Google. Some interesting results that I've seen, particularly in Germany on cryogenic as well. But thank you for the response. It's good to know and get an idea as to how everybody is doing this. Okay, so
Yeah, let's go back to we can just talk about those different approaches. I see no one who voted for MQL. Perhaps we need to explain what that is. Yeah, obviously most people are using flood. It's the most common form of coolant. Yeah, it's relatively effective. But yeah, as Peter told us about, we have a lot of problems coolant depending on which one you use. You're always going to have to eventually throw it out and replace it as it starts going rancid, starts becoming too clogged with chips. So yeah, then in terms of sustainability, you can look at dry cutting because of course there's no coolant material there. So there's nothing to dispose of, nothing to contaminate waterways. But of course with dry cutting, the only heat production there is through the chip extraction. You're going to have a lot of heat buildup. So you're not going to be able to take particularly aggressive cuts. You're going to have to be quite conservative with your cutting. Yeah, much smaller cuts. I suppose you don't want to reduce your speed too much, or it's going to still have heat buildup. But yeah, of course, heat buildup, as Peter said, it's going to distort and degrade your materials, and it's going to increase the wear of your tool as the tool heats up. The cutting flutes get a bit softer, and it allows them to dull faster. These are the last two strategies. So MQL stands for minimum quantity lubrication. So what people have found is that the coolant is only really effective when it comes in contact with the point where the tool is making contact with the part. In flood, all of that coolant that's spraying all over the place, most of it's not doing anything. So what MQL does, you can see the nozzle in the image, it's directing a stream of compressed air mixed with a small amount of oil. So it's just focusing that bit of oil, and it's mixed with a few other additives to create a good coolant, but it's using far less material than conventional flood cooling. Yeah, so there's a lot less material, it's a lot less sort of complex of the material. It's just you could even use a kind of mineral oil that's being sprayed onto that cutting point, so you're getting coolant that's as efficient as flood cooling, but using far less material. So yeah, there's not so much to be cleaned up, a little bit of oil on a metal part. It's not a lot to clean up before you're doing your whatever finishing processes you might move on to. Then lastly, cryogenic. Yeah, this is the one that sounds very futuristic. Maybe we're thinking of Star Wars and some carbonite. But yeah, this is using nitrogen, liquid nitrogen, to supercool the part. So we're dropping it to below freezing temperatures. The whole part is, you can see it's very cold. The tool is also getting cooled massively. So we don't have that heat buildup that we have. So the tool is going to stay sharp. It allows us we can increase our cycle times, the speed of cutting, by between 40 and 400%. We can increase the speed because there's no heat buildup because it's so cold. And this works well on hardened steels. medical alloys and aerospace super alloys, works with those, and then even some polymers such as PE, EK, and silicon. So it's quite a versatile cooling strategy. Yeah, it also, apart from increasing your cycle time dramatically, it will also improve the finish of your machining on your part. Right, yeah, as the last point, again, going back to the Fusion Post processor, if you are implementing these kinds of more advanced cooling strategies, perhaps it's something you need to add on to your machine, then yeah, Fusion allows for custom code to be generated, putting the necessary codes for these different kinds of cooling strategies. All right, next one is green tooling. What is green tooling? Peter is going to take us through that.
Green tooling, yeah, interesting one. And it does exist, it is a thing. And I would recommend, I'm actually just going to give examples of green tooling. Luckily, I think most of the major suppliers are manufacturing tooling in a sustainable way. It seems to be quite a common thing worldwide. And by the looks of things, your main sort of tooling guys all seem to be jumping on board. For example, high hardness and wear resistance. So cemented carbide tools are extremely hard and resistant to wear, making them ideal for machining tough materials like steel, stainless steel, and high temperature alloys. Due to the hardness and the wear resistance, cemented carbide tools have a longer lifespan compared to tools made from conventional materials like steel or high-speed steel. This reduces your tool replacement frequency and downtime. Now, the whole point is here is that the next tooling, the longer your tooling lasts, the more of it's being thrown away, or the less of it that's being thrown away on a monthly basis or a daily basis, depending on your workshop. Carbide tools also maintain their dimensional stability and cutting edge integrity, even under high cutting temperatures and speeds, leading to improved machining precision and giving you a much better surface finish as well. Cemented carbide tools can be used across a wide range of machining operations, including turning, milling, drilling, as well as cutting, due to their ability to withstand various cutting conditions and materials. They also have a very good resistance to thermal deformation. Conductivity and resistance to thermal deformation, which helps in maintaining dimensional accuracy, avoiding tool failure during high-speed machining. We are going to touch on high-speed machining a little bit later with Michael. And again, there is tooling available that will obviously go with these kind of tool paths as well. The caveat is, yes, these tools, despite the initial cost, cemented carbide tools can reduce overall machining costs by improving productivity through faster cutting speeds, longer tool life, and reduced scrap rates. So the whole point is you buy a more expensive tool. Initially, yes, it costs more, but if you're doing a high production job, for example, and that tool lasts longer, you're not only going to make your workshop more efficient, you're going to be throwing away less tools, and obviously these all add up to being better for the environment as well. Carbide tools are also well suited for high-speed machining applications where your cutting speeds and your feed rates are increased, something we're going to cover a bit later, thanks to their heat resistance as well as their hardness. Like we were saying, the environmental benefits, it's highly recyclable, and recycling programs for carbide scrap help in reducing the environmental impact associated with mining and processing of raw materials like tungsten and cobalt as well. Okay, so what happens if we lose less tooling? What are the actual benefits here? So it's going to reduce the need for extracting raw materials from the earth, which helps in preserving natural resources as well as habitats. Energy conservation. Recycling typically requires less energy, so it's actually costs less and requires less energy to recycle something than actually just having to go and process, dig the material out the ground, and constantly make new ones as well. This will obviously lead to lower carbon dioxide. It also has an effect on our CO2 rating, contributing to climate change mitigation as well. We also need to talk about ethical sourcing. Recycling will decrease the demand for new materials, including, again, like we discussed, cobalt, which often come from mines which have questionable ethical and environmental practices. This promotes more responsible sourcing practices and supports sustainable development goals. As you mentioned, Cyril basically wrote a new one into law just the other day. Resource efficiency. Recycling extends the life cycle of your materials, promoting a circular economy where materials are used and repurposed rather than just being constantly thrown away, thereby maximizing resource efficiency. Try and put back what we use to be reused again as well, and create that kind of cycle instead of just use it, throw it away into landfill, dig out more at the ground to make new ones the whole time. It's something that really needs to be worked on. Promotion of innovation. So recycling will also encourage innovation in technology and processes aimed at improving efficiency and reducing environmental impact in material recovery and reuse. Sorry, just go back there. Okay, the last one I wanted to talk about there is job creation. This is going to be, the more people recycle, the bigger that industry is going to get. It creates jobs in collection, in sorting, in processing, as well as the manufacturing of recycled materials, contributing to economic growth as well as sustainability. Okay, it's up on the screen here. I've just given the sort of wide variety of the general type tooling that most of the guys will use. So cutting tools made from recycled materials like carbide inserts, coated tools that extend the lifespan of your tooling. In other words, the ones that are slightly more expensive but last longer. These are designed by most of your tooling suppliers and obviously are designed and manufactured in such a way that they can be recycled after use. There's also guys that are doing non-toxic coatings and finishings. You know, tool and dies coated with non-toxic or low VOC, which is VOC finishes that provide corrosion resistance and durability while minimizing environmental and health impacts. If you don't know what low VOC is, it refers to volatile organic compounds that are not harmful to the environment as well as to humans. Okay, next up is sustainable materials. I'll hand over to Michael.
All right, yeah. So the next thing we can have a look at is what materials we are using to machine our parts out of. Yeah, Peter spoke about what materials we're using for our tools, but of course, much greater volume of material is going to be from the parts that we are actually making. Okay, so what are the attributes of a sustainable material? Of course, a material that is recyclable once it's been used, or if you have a waste part that's unusable, it's important to choose a material that can be recycled. Then, of course, it's important to choose a material that is recycled. It's all well and good that your parts can be recycled after they've been used, but even better is if we're using the material that we're using has already been recycled. So it's continuing the cycle of use, that we're not continually using virgin material that has been mined using very high energy intensive processes. Then another aspect, which is in some ways related more to design, is that the part is reusable. I suppose if we can consider plastics, obviously a very high pollutant in today's world. If we consider making products that are reusable rather than the ones that we are just going to throw away after a single use. So that can also be extended to mechanical parts. Is this something that can be reused and repurposed? Because it's something that can be, does it have parts that can be easily replaced to improve the longevity of our products so that we're not just throwing them into the scrap once they've reached if something is broken, if they're no longer usable, it's much more sustainable to consider repairing that part than buying a new one. Okay, and then Peter is going to talk a bit more about various materials and their sustainable properties.
Okay, so what I've noted is a few examples of sustainable materials. Luckily, a lot of these materials are in use currently. Yeah, a lot of the guys are manufacturing these kind of materials. So I thought I would just note a few examples of good materials to be using. Generally, it's down to the client. They wanted to machine out of a certain component, you're going to machine it out of that. But there are good ones out there. Here's some examples. Aluminum or aluminium, depending on where you are in the world, is lightweight, it's recyclable, and it's widely available. Very common. It requires less energy to produce compared to other materials like steel, for example. It can be easily recycled without losing its properties as well. This makes it a good sustainable choice for various CNC machining operations as well as applications. Brass, very common, is an alloy of copper and zinc. It offers good machinability and corrosion resistance. It's also recyclable, which contributes to the reducing environmental impact. Brass is commonly used in CNC machining for parts that require good conductivity or aesthetic appeal, because it does look good when it's machined. Engineered woods, sustainable woods, such as bamboo, reclaimed woods, or there's a company, if you Google it, called FSC, Foxtrot Sierra Charlie, South Africa. Certified wood, it stands for the Forest Stewardship Council of South Africa. These are used in CNC machining for applications like furniture, signage is a good example, as well as decorative elements. These woods come from responsibly managed forests or are made from rapidly renewable resources. Bioplastics, these are derived from renewable resources such as cornstarch, sugarcane, or cellulose. They're becoming more popular in CNC machining for the guys who are actually doing on plastics, even for 3D printing, for rapid prototyping. I'm seeing a lot of 3D printers popping up now where the guys want to just check if a bracket's going to fit, especially for the guys that are machining components that are going onto equipment that sits in the field. Those holes don't always line up. So it's quite handy having a 3D printer on site that you can make a quick one, make sure it's going to fit before you machine the final one. But obviously bioplastics, these offer biodegradability or recyclability advantages over traditional petroleum-based plastics, which you buy new, and these are great for sustainable rapid prototyping. There's also recycled plastics, so plastics made from recyclable materials such as PET or HDPE, which is high density polyethylene. These can be machined into machined parts while reducing the need for virgin plastic production, in other words, making them from new all the time. These materials will help divert waste from landfills and conserve our natural resources for all of our countries. Titanium looks good, it's also lightweight. It's a strong material that is highly durable as well as being corrosion resistant. It does require more energy to produce than aluminium, for example. Its long lifespan and ability to be recycled make it a sustainable choice for CNC machining in industries like aerospace as well as medical. Titanium is very common in those two industries. Cast iron, it's got excellent machinability and durability, making it sustainable for heavy duty applications in machining. It's also highly recyclable, which helps reduce your environmental impact. The last material I'm going to note here is ceramics. Advanced ceramics such as alumina or aluminium oxide. These are used in CNC machining for applications requiring high temperature resistance, wear resistance, or electrical insulation, for example. These materials are durable and can be recycled or reused as well. Okay, so next up we're going to be looking at high-speed machining. We basically said a little bit earlier that you can select your tool, you can set your speeds and your feeds in the software to get your machine time using things like high-speed machining as an example. I'm going to hand over to Michael. He's going to take us through a little bit on high-speed machining.
All right, cool. Thanks for that, Peter. All right, so we've looked at a bunch of different factors that can improve to improve the sustainability of our workshops and our CNC approaches. Now, we're going to have a look at how we can actually change our machining strategies, our toolpath strategies, to improve efficiency and to improve sustainability. So, high-speed machining. This is a relatively new concept that is becoming more widespread in its use. So here we can look at these diagrams where we're showing traditionally, if you want to be safe, you don't want to risk your part moving, you don't want to risk tool breakage. So you're going to go with a shallow step down, maybe a larger step over, a larger radial pass. But we're going to do a number of shallow step downs, which of course results in concentrating all of the heat and the wear on the tip of the tool. So you've got a high heat buildup, which will again degrade the life, lessen the life of your tool, start causing it to blunt faster. It'll also increase the heat on the part, so that there's more risk of deformation or of the material losing its properties due to excessive heat gain. As a solution to that, we can look at this high efficiency or high speed milling. Also we're going to try and instead of doing several shallow cuts, we're going to do fewer deeper cuts using the entire flute length of the tool, and we're going to do shallow radial passes. So this, as you can see in the diagram, it spreads the heat gain over the entire length of the flute. You're using a larger length of your flute, so there's more of the tool engaged. So it's going to improve your tool life. There's not going to be as much wear because you're using the whole tool at once instead of just the end. It will also increase and potentially increase the accuracy of your machining because there's less deflection of the tool because you have the whole tool engaged. So it's a much stronger full tool is engaging at one time, and there's less deflection on the tool. Here we have an example of the traditional machining. You can pay attention to the machining time. Here we're doing several shell. We've got 3, 4, we've got 6 passes there to complete this machining with what we've decided is the adequate load for the tool. So we're happy with that step down. That's not going to shift our parts, it's not going to break our tool. So this seems fairly reasonable, but if we look at this machining time, it's not on the screen now, but we'll have a look next at high-speed machining strategy. Yeah, here we're using high-speed, high-efficiency machining. So we're engaging the full length of the tool. We're taking those shallow cuts, which is about the same amount of material per cut. But if we look at how long this takes, it's about half the time as the previous video was, and they were both running at the same feed speed. So yeah, this is definitely a good strategy to use. We improve the life of our tool. We improve significantly the speed of our machining. So the machine is running for a shorter time. It's resulting in less energy usage by the machine. Yeah, and also we'll have improved finishing of the part because we're machining a single pass. We don't have multiple passes where we could risk seeing a tiny step. We're going to have nice, clean edges. Yeah, so this is definitely a very good strategy to look at employing. And Fusion has included in it. It has the strategy is called adaptive clearing, adaptive milling, which is optimized to do this kind of full flute high-speed machining. Right, and then Peter has an example, further examples of this adaptive clearing, and he's going to take us through that.
Thank you, Michael. I know people are busy, so we're going to pick up the pace a little bit here. But what I'd like to show here is you have your 3D tool parts. There's contour. You set your tool to the left or the right of the tool, you height your depth, and send it. No chamfer. There's 2D tool parts, and then there's 3D tool parts as well, which are the smart, aware, remembering stock remove your previous operation tool parts as well. A little box called rest machining. And Michael was saying, these kind of tool paths are designed in such a way that you get less material waste. So it's going to automatically optimize your tool path to minimize material removal, reducing the amount of waste material generated during your machining operations. This efficiency is going to help conserve your raw materials and reduce the overall environmental footprint associated with material extraction, as well as disposable, requiring no skill level for the person programming the component. So something like adaptive clearing, this is an automated 3D toolpath. So in most cases, as long as your setup is correct, so you've made sure that your stock is correct, you've got the right tool, Fusion's going to pretty much do the rest from you. So it's not like it's a massive change that you now have to relearn how to do machining. These 3D toolpaths are amazing. If you have used Fusion in the past, haven't used it, still looking to do it, you can download free files for it. Go and give these 3D toolpaths a shot. You can still go and edit them, because obviously understandable. You don't want to have high-speed machining maybe on your old CNC machine that's been there for 30 years. It's understandable. So these toolpaths always calculate to be efficient, and then you can always go and edit and change them afterwards to get it to match your machining conditions that you use in your workshop. But again, the more efficient your toolpaths, it's going to lower your energy consumption. So again, it's going to reduce the amount of material that needs to be machined away. Adaptive clearing can lower overall energy consumption during machining. This is particularly significant in industries where energy-intensive machining processes are common, especially for high production where machines never stop. Saving 1 minute on a job for a roughing operation when you're making thousands, that's going to add up to a lot. It's also going to then extend your tool life, obviously, like Michael was discussing earlier. Get the proper tooling that you can take full flute depth cuts. You're not putting all that heat into one little small area. Again, less energy. It's going to have a knock-on effect of reducing your CO2 emissions. It's going to improve your efficiency. And by doing all of these things, you are going to be supporting sustainable practices for the environment moving forwards. Okay, so key takeaways out of this, we've been hoping that we've maybe raised awareness a little bit on the importance of sustainability. Something like Fusion or CAM software can actually help you to achieve these goals, especially if you guys are still going manual. There are massive plus points to going for CAM. Gives you foresight to be able to see what's going to happen before it actually happens. And the last point we've noted there is it's easier than you might think. Software is very smart these days. These guys know what they're doing, and these toolpaths and obviously functionality within these CAM software packages. This is made to make you more efficient. They're made to do these kind of things automatically for you. I think the next one, we want to just see if there's any questions. If you guys do have any questions, please feel free to put them in the little chat box below. And then on the whilst we're doing that as well, I think I'm going to put the next slide up for Michael to talk about his ebook.
Yes, yeah, sorry guys, we're running a little over time, so we'll go through these last ones quite quickly. But if you follow this QR code, it'll take you to the Baker Baynes website where our transformation tools are. So most of the information that's in the slide, plus more information in this presentation is compiled into an ebook that you can download for free, and you can refer back to all of these recommendations that we've made. Yeah, and as a call to action, yeah, there's a serious need to implement sustainable practices. Yeah, you're welcome to reach out to us at Baker Baynes, where we can provide you with support to have a look at these options that Fusion gives you to improve the efficiency and sustainability of your machine operations. Yeah, there are contact details.
Okay, let's just check whether there are any questions.
I think, yeah, so the question is, using the supercooling cryogenic method, how does the workpiece not become brittle, and how is this controlled? I think to answer that question, there may be a sort of only certain parts, certain materials that can be used effectively with this, using perhaps a mild steel or brass. If we supercool it, it's going to become a bit more brittle. Yeah, there's a limited number of materials that are appropriate for this cooling method, unfortunately. Yeah, thank you for your question. Thanks everyone for their time. Yeah, I really hope that we've given you some food for thought to think about ways that you can improve the sustainability and efficiency of your machining workshops.
Great. Thank you for joining us, everybody.